back to my channel, and today I'm going to be talking about some formulas for systems of linear equations and indeterminate equations. So let's begin by talking about systems of linear equations. So what is a system of linear equation? To truly understand what a system of linear equations actually is, we must talk about the main objective or purpose behind the system of linear equations. So we're trying to find what is it trying to achieve. Now, a system of linear equations is usually shaped like this. We have ax plus by equal to c, representing one line, and we have kx plus qy equal to d, representing another line. So as you can see, these two lines we can use to our advantage, and using the methods of elimination or substitution, we can isolate the values for x and y. That's our main purpose. But why are we isolating the values of x and y? And how does this relate to the graphical interpretation of these lines? Well, to truly understand that, we must talk about the main purpose behind each of these lines. So we have to talk about their graphical versions. So let's just draw a coordinate plane. Just draw a random intersection of two lines. As you can see over here, they intersect at this point, which we'll call x, y. Now, in a system of linear equations, we're trying to use both of these lines to isolate the values of x and y. So let's call this line k, or let's call it rather f, and this one g. So f sub e will be the equation for line f, and g sub e will be the equation for line g. Using methods of elimination or substitution, we can obviously find the answer to this, which will just be x equals something and y equals something. Now, these values will correspond with the point of intersection, because the point of intersection satisfies both of these equations. So if we take x and y and plug it into both of these equations, it will both satisfy, because they individually cross through this point. So that's why this is called the solution point or intersection point. So in reality, at the fundamental level, a system of linear equations is trying to essentially isolate or find the values of the intersection points. Moreover, trying to find the coordinates of the intersection points. Okay. Now that we have talked about that, let's move on to the formulas with an emphasis of linear algebra for the system of linear equations. Now, usually when you're taught in an algebra class, you're either taught one of these two methods, elimination, substitution, and most likely you're taught both. Now, you can use elimination or substitution to essentially try to find the solution to a problem. But elimination is a process, and this process has a step-by-step things of what you have to do. And even if it's a process, it's not a definitive process, because by a definitive process, I mean that it says first, take ax plus b or something, or multiply things by 4 or something. It doesn't say that. It gives us a choice depending on the equations. So it's a rather arbitrary process, ambiguous process. But we use these fundamental principles to isolate the specific answers. But this makes mathematicians wonder, is there a specific formula to find the solution? And yes, indeed there is. And this is in terms of linear algebra, because it is a lot of relationships with determinants, which I'll talk about a little bit later. So let's first talk about more of the specifications between the original equations we saw earlier and the equations we have over here, because over here they look a lot different. Okay. So first, as we have over here, we're going to substitute x1 to equal x, b1 to equal c, x2 to equal y, and b2 to equal d. Now, this means that we substitute x1, x2 to equal x and y, and then b1, b2 to be c, d. Now you may be wondering, what about a11, a12, a21, a22? And you also might guess that this is probably the coefficients. And yes, indeed, they are the coefficients. But why this specific terminology? The reason is because they correspond to a part in a matrix. In a matrix, we have the form Aij. When you're taking linear algebra, you commonly interact with this specific type of format. Now this, by the way, is not a matrix, it's the determinant. We will talk about these more a little bit later. But this is how it's represented. In linear algebra, you deal with vector quantities, you deal with determinants, matrices, transposing them, trying to find some specific things. You might even deal with some number systems in a sense. So linear algebra is a broad field. Okay, so now let's come back to this. What this actually represents is that we have A, which we'll call the value. So A will be considered the value. So if we say Aij, we're saying, oh, okay, we're dealing with the value in a matrix. But we want to know the location of this value in the matrix. Well, we'll write Ij. I is equal to the rows, and j is equal to the columns. In doing so, we can isolate each value. So if we say A11 in a matrix, for example, like this, we mean first row, first column, and that's this. If we say A21, we mean second row, first column, which is this. So A21 equals 3, and A11 equals 6. So as you can see over here, this is how these actually work. So these are essentially going to be the coefficients for x and y's, but they have a deep underlying meaning. They correspond with this specific type of matrix. And they have the specific points over here. We'll talk about how that matrix relates with these formulas a little bit later. But okay, let's actually start to analyze these formulas and how it relates to a determinant. Now let's actually talk about how we evaluate a 2x2 determinant. I've created a video on how to evaluate determinants, specifically through unorthodox methods, or unorthodox methods to a person just slightly reviewing linear algebra. When you're in deep algebra, there are actually methods that you usually see. So I have a video on determinants and a video on just regular matrices and determinants, how to calculate using the standard way. Okay, well let's review how to calculate 2x2 determinants. So let's say we have 6, 1, 4, 3. To calculate this, the determinant, we would have 6 times 3, which is 18. 18. Subtract by 4 times 1, that's going to be 4. So we get 14 equal to 6, 1, 4, 3. Because we have 6 times 3 is 18, 4 times 1 is 4. 18 minus 4 is going to be 14. This is going to be the determinant of this matrix over here. Notice that these are the symbols for a determinant. A matrix we can write like this. Okay, so that's how you calculate a determinant. You do the principal diagonal, multiply, principal diagonal first, and then you do these, and this is going to be the regular diagonal. So it's P D minus D equals determinant. And this is for a 2x2 matrix. Once you have a 3x3 matrix or 4x4 matrix, things become a little bit more complicated. Okay, so now let's look at these formulas. So we have x1 equal to b1 times a22 minus b2 times a12 all over a11 a22 minus a21 a12. Now one thing you might realize is the denominators are both the same. And sometimes when you're doing systems of linear equations, when you eliminate using elimination, you see that the denominators are most likely, most of the time, are going to be the same. And actually we can see this in this specifically. So let's first talk about the denominators because they have an underlying key principle that we must understand. And they do indeed relate to the matrix. So let's focus back on the coefficients. Write this the coefficient matrix. We'll call it the coefficient matrix because it has all the coefficients. So A11, A12, A21, A22. This will be a coefficient matrix. A11, A12, A21, A22. So for each equation, the coefficients, so this will be x, y, and this will be y1, y2, x2, x. So these will be the corresponding places. Okay. So now that we have this coefficient matrix over here, what happens if we take the determinant of this? So instead, let's erase the matrix marks and just write a straight line for the determinant. Now let's just erase these subscripts. Okay. So what we'll have is this. Well, essentially, the determinant is going to be A11, A22 minus A21, A12. And this indeed will be our determinant. So as you can see over here, the determinant is just going to be the denominator. So the coefficient matrix, which we'll just call it right now, the determinant of all the values, or all the coefficient values, is going to be the denominator. That's one thing to realize. That's an important key aspect. Notice that this works for both x1 and x2, or x and y's. Okay, now let's talk about the numerator. So let's first talk about x1's numerator. So we have b1, a22, then minus b2, a12. This also corresponds to a determinant. Now, we already talked about this determinant, which is going to be the denominator. So it has to be this or this. If we evaluate them, we see these match. So that means this is going to be the determinant. b1, a12, b2, a22. Because we have b1 times a22 minus b2 times a12. This will be precisely that. So as you can see over here, this determinant is just going to equal to this over here. So that's actually pretty special, because it's interesting how we just have different determinants. And if you think about it more, we can see how b1, b2 are involved. But also we have a22, a12. So it's like we take the kind of like the determinant of these values. So it's like we take the determinant of this to be our denominator, the determinant of this, and the determinant of this, which we'll just see next. Now that we've talked about that, let's look at the last scenario, or the last numerator for y or x2. So you have a11, b2, minus a21, b1. Now over here, this probably corresponds to a matrix, and indeed this corresponds to this one, determinant of the matrix, more specifically. So as you can see over here, we write this, a11, b1, a21, b2. We have a11 times b2, then minus a21 times b1. Okay, so this is going to be our specific answer for the determinant, and indeed this is going to be the numerator over here. So as you can see, these are all determinants of matrices. So as you can see, using the formulas, which are these, so pretty much now that you've identified that this is going to be the equation or system of linear equations to be written in a more complicated but also simpler form, these are going to be the formulas, and you can actually use them, and they actually do work. And now we just talked about the underlying linear algebra purpose of determinants. We can even write x1 to be b1, a12, p2, a22, which is determined all over a11, a12, a21, a22, and x2 to be a11, b1, a21, b2, all over a11, a12, a21, a22. We can even write them like in a determinant form over here. Okay, now that we've talked about that, let's move on to indeterminate equations. Now, indeterminate equations are actually pretty easy. The reason they're called indeterminate equations is because you don't have enough information to essentially just get a single definite solution. We have an infinite solutions. We don't have enough information to just say that we have these are all the possible solutions using a specific formula or just anything. There are like infinitely many solutions to them. Now over here we have the formulas for an indeterminate equation. So ax plus by equals c can be considered also an indeterminate equation. Reasons because we don't have enough information. The formula for these are x, the x is equal to little a minus bt, and then y is equal to capital B plus at. Now, notice that this equation must be free from fractions, and a and b, little a and big B, have to be integral solutions. Notice that a and b must be a solution that we can just plug in and check in value. They have to be integral values, but it's something that we automatically know satisfies the equation. Then b, we already know, is given it to us in the equation, and a already is given to us in the equation. Now, in these, if we just find these formulas, we can talk about all the values, infinitely many values for this equation. So that's actually very powerful. Just using two simple formulas, we can find all the solutions to this indeterminate equation. Let's check. So we have 4x plus 2y equals 5. So let's find a solution to this. Well, if we state that we have, well, let's do something like 7, because then we can just say x equals 1 and y equals 1. So we wouldn't have much fractions. Now we obviously can see because 1, so 4 plus 3 is 7, so x and y equal to 1. But there can be more solutions to this, but let's just see. So x will be little a, so we have 1 minus b, which is 3t, and we'll write this over here. B, which is 1 plus at, 4t. This is going to be x, and this is going to be y. Notice that t can be any integer we can plug in. So let's plug in 1. So 1 minus 3 is minus 2. 1 plus 4 is 5. 4 times 5 is 20. 4 times minus 2 is actually going to be minus 8. Minus 8 plus 15 is 7. It works. We can keep on plugging integer values for t and get all the solutions that satisfy this equation. Okay, so now that we've talked about indeterminate equations, we can make this video to an end. If you like this video, if you like this channel, please subscribe to learn more. Thank you.